All right, okay, well, good morning, everyone. Today we're going to continue with a class of looking at elasticity. And actually, I hope that today we get to cover two very important application examples of the theory of elasticity. One, for predicting what is the horizontal stress at a given depth in the subsurface. And two, to calculate what is the pore compressibility of the rock that you use in reservoir simulation. I know that that's a parameter, you have an idea about what permeability could be. You have an idea about what viscosity of the fluid might be, but compressibility, that's kind of always a shady parameter that you don't really know where it comes from. So we're going to try to explain that. We're building up into solving elasticity problems in physics. And in order to do that, we found out and we defined actually what the Young modulus is and what the Poisson ratio are. And by now, you have all done the first lab in which you calculated the Young modulus, right? Do you guys remember more or less what was that Young modulus for your rocks? You had to calculate one example, right? Anyone? No? No? You don't remember? You didn't calculate that? No? Oh, I'm gonna talk to Jeffrey. You should have calculated that. But you should see the value which is more or less between 1 and 10 gigapascals, which is more or less a little bit less than 1 million psi and probably 2 million psi or something like that. All right. Okay. So we define Young modulus. We define Poisson ratio. This is what you did in lab. Later on, we're going to talk about peak stress, but we didn't get quite there yet. We're talking in the regime in which rocks deform and stress is proportional to strain. And in order to understand stress in 3 dimensions, we talked about the stress tensor. What stresses are in 3 dimensions, normal and shear stresses, and how we write that as a matrix. And we further went into the concept of principal stresses. Most times, we're going to work mostly with principal stresses because it's just easier to work with that. But remember, if you're given or you're working with the value of principal stresses, you need to know what is the direction of those principal stresses. Otherwise, your information is incomplete. But as long as you know the values of principal stresses and the directions of principal stresses, then you're good to go. And if you want to compute what is the effective stress tensor, you just subtract to the total stress the value of pore pressure in the diagonal terms. Why? Because fluids cannot apply a steady state or a steady shear stress. Okay, so this was just one more example of stresses. So we have talked a lot about stresses, but actually in many of these problems, in order to solve them, you need to know something else. This is what is called in continuum mechanics an overdetermined problem. And when you have an overdetermined problem, you need additional information in order to solve it. And in that case, that additional information is going to be the other side of the stresses, which is strain. And we have already worked a little bit on strains. So if you remember, when we apply stress, it deforms, and the change in length is what we define as strain. The change in length divided the original length. Okay? So let's kind of generalize this now to 3 dimensions. All right? So if you were to, we're going to call this, we're going to start talking about strains. And if you were to imagine a solid in which this is axis 1, this is axis 2, and axis 3 is coming out perpendicular out of the paper. And if you had a solid which is originally a cube, now we just see one face of the cube, okay? But if you had this one, and this one had an original length, how should I call that length in direction 1? Let me call it dx, but it's going to be dx1, right? Because it's in direction 1. And if I were to stretch now this solid, if I wanted to pull from this face to the right, that solid could be formed into this new shape, and we're going to have displacement, which we're going to call du1. The change of length divided the original length is what we call a linear strain, and we're going to call epsilon 1,1. Why? Because it is the change of length in direction 1 divided the original length in direction 1. That's why it's called epsilon 1,1. In the same way, for example, if you had here the same thing, but now you pull in direction number 2, only in direction number 2, and now the new shape looks like this. So let me just make clear that it's everything, okay? So this one remains attached to the, in this case, to the bottom face. And now look, I'm writing this is going to be dx2, and this is going to be du2, and epsilon 2 is just going to be du2 divided dx2. It's the same thing. You could do it also in the third dimension. It's going to be exactly the same. Notice that this strain is what sometimes is called a linear strain, or also it falls into the category of a volumetric strain. And why do you think it's called like that, volumetric strain? Because the volume is changing. The volume is changing. So with that kind of strain, you change the volume, the original volume of the solid. And we're going to see an example in which, with some other kinds of strain, you do not do that. So for the third case, and this is always a three-dimensional solid, remember, but I'm just simplifying the drawing here to be a little bit easier to understand into just a projection with an axis perpendicular to the paper. So we're going to have still the same solid, but now instead of pulling from it from a side, I'm going to apply shear stresses to it. And those shear stresses, what they're going to do, I'm not going to write them because I don't want to make a mess in my drawing, but I'm going to explain that in a bit. They're going to deform the solid, which is going to look now so what kind of stress do I need in order to do that? Probably I can do it here in the top, okay? So I don't mess up my drawing at the bottom. It's a pure shear stress which looks something like this. So can you see that if you were to do a vectorial summation of these two, it's going to pull in this direction, and we do a vectorial summation of those two, it's going to pull in this direction. So it's in a state of stress that pulls in this direction and compresses in that direction. And as a result of that pure state of shear stress, now you have a distortion of the solid. Notice that what was before a right angle is not a right angle anymore. So there is a change in the shape of the solid, but there is no change in volume. Probably you could tell me, no, that volume is not going to be the same. And probably in that drawing that's right. But if you were to consider very, very small deformations, that change in volume is going to be very, very small and almost negligible. So in order to quantify this distortion angle, what we're going to do is we're going to calculate this angle over here. This distortion angle that we might call it, let's call it theta, okay? And what is the tangent of that angle? Well, you will see that here, for example, if I were to look at that point over there move an amount du1 in direction number 1, and it was originally somewhere over here where the length, what is the length? What is that length? That one is dx2, right? So here the tangent of that angle theta is just du1 divided dx2. So you see that now, before we were taking displacements and dividing the length in that direction, but now we're taking a displacement in one direction dividing the opposite direction, in perpendicular direction to that one. And that gives you an angle. For very small angles, we know that theta is going to be more or less just the ratio of those quantities. And similarly to that, let's look at this other angle. This other angle, that point over there, move a distance du2 in direction 2, and the angle is going to depend on that displacement and this original distance dx1. So if I wanted to consider those two angles, which in this example are the same, what I can do is I can take an average of that, and I'm going to say that the average of du1 divided dx2 plus du2 divided dx1 is what I'm going to call the shear strain epsilon 1, 2. And now this one is a shear strain, which implies no volume change. And similarly to the strain tensor, I can also write a strain tensor, and it's going to be very similar to the stress tensor, but populated with strains instead of stresses. So the strain tensor epsilon is going to be equal to epsilon 1, epsilon 1, epsilon 1, Notice that now we have a shear strain in the plane 1, epsilon 2, epsilon 2, and epsilon 3, and this is also same as the strain tensor, is symmetric. So I'm now going to write the lower part below the diagonal, and it's going to be also filled with real numbers. It's going to be also principal values in direction, the same as the stress tensor. And if I want to fully write this in terms of displacements, this is going to be du1 dx1 1/2 of du1 dx2 plus du2 dx1 1/2 du1, what is going to be here? dx3, right? du3 dx1, and this is going to be du2 dx2, and this is going to be du3 dx3, and this is going to be du2 dx3 plus du3 dx2. I'm going to come back later on. I'm kind of skipping something here, but notice that here we're talking about displacement. U is a displacement. And we're going to see later on, we're going to see an analogy of how, for example, when you solve a fluid flow equation, what do you solve for usually? Do you remember in Reservoir 1, Reservoir 2, probably Reservoir 3 too, when you're solving a fluid flow equation, what do you solve for? You know the far field pressure, you know the bottom hole pressure, so what do you solve for? You solve for pressure, right? You solve for the change of pressure from the wellbore to the far field. And then you know, when you know the change of pressure, you know in which direction the flow is going because it's going in the direction of the maximum change of pressure. But you solve for pressure in a fluid problem. Similarly, in a mechanics problem, you solve for displacement. And with those displacement, you compute strains. And with those strains, you compute stresses. We're going to get there later on. Okay, I think then we're good for now with strains. Very similar to the stress tensor, then we have the strain tensor. And now we're going one step further. You know that, as we did in the example before, if I were to push this with my hands, I'm pushing very hard. Probably you can see, but I'm pushing very hard with my fingers. The amount of strain that the solid takes is proportional to the amount of force or stress that I put with my fingers. So there is going to be a relationship between the strain tensor and I'm going to call it now D, okay, between the strain tensor and the stress tensor. This is very similar to saying this is a typical Hooke's equation where epsilon is divided sigma by E, right? This will be Hooke's law 1D with the stress. I'm writing something very similar here, but it's valid for 3 dimensions. So let me think how to put this into, to give you an example, but well, don't worry about the example. We have a problem here. And the problem is that here we have a matrix, which is 3 by 3, which is that one. This sigma is another matrix, which is 3 by 3. The element in here that allows us to do this multiplication is something that we cannot write on the paper. It's like drawing in paper a 4-dimensional entity. It's not possible, okay? Or a 5-dimensional entity. It's not possible. It's the same with this guy. This guy is something which is called a 4th-order tensor, and it cannot be drawn in paper. It cannot be written in paper. So we're gonna take we're gonna do a simplification, which is not going to change anything. It's just an easy way of writing this same mathematical operation. Okay, and this is what is called Voigt notation. And it's used a lot in geophysics and in mechanics. If later you go and work on wellbore evaluation, formation evaluation, and you work with acoustic logs, you will see a lot of these relationships for understanding elastic waves in rocks. So what is the concept here? The concept is that this strain tensor over here, I know that there are 9 components, but there are just 6 which are independent. And because there are just 6, I'm just going to write 6. And instead of writing it as a matrix, I'm going to write it as a vector. So I'm going to say that the strain tensor epsilon is going to be epsilon 1,1, epsilon 2,2, epsilon 3,3, and I like here to add a line which is going to separate the linear strains from the shear strains, and here I'm going to write epsilon 1,2, epsilon 1,3, and epsilon 2,3. So those are the 6 independent elements. And here I'm going to write the stress tensor. There's going to be something here. We're going to talk about that in a moment. But you can already see it's large, and we don't know the values yet. But the same way with the strain tensor, with the stress tensor, here we're going to have sigma 1,1, sigma 2,2, sigma 3,3, and those are the normal stresses. And here we're going to have sigma 1,2, sigma 1,3, and sigma 2,3. By convention, and just this is something that we're just making up ourselves to make our life easier later. Here, let me delete this line. Usually instead of epsilon 1,2, we like to write here 2 times epsilon 1,2, epsilon 1,3, epsilon 2,3. But all of the rest is the same. Okay? So the same as I had some lines over there, I'm going to add also these lines over here. This is going to separate this matrix into 4 parts. So what is going to be the size of this matrix? This is 6 by 1. This is 6 by 1. So the matrix in here is going to be what? It's going to be 6 by 6. Okay? So we need to find out the values in here of 36 coefficients. It's not going to be that complicated, don't worry. In order to fill up this matrix, we're going to do the following. I'm going to bring back what we have already done last week, which is this test. I'm going to generalize that for 3 dimensions. And then we'll come back to the matrix. So according to this kind of test, if I apply a normal stress sigma 3,3, I'm going to get this. Look, I apply 1 stress, I get 3 strains. I get sigma 3,3, sigma 2,2, and I get also epsilon 1,1, which is over there. So let's look at this example. So what is going to be the value of epsilon 1,1 for that test? And I'm going to try to find all of them. Epsilon 1,1 is going to be equal to minus the Poisson ratio epsilon 3,3. Can you see that? And let me write it so it's clearer. So these equations are the same as saying that epsilon 33 is equal to sigma 33 divided Poisson ratio, right? Just simple operation over there. And this equation allows me to say that epsilon 11 and epsilon 22 are equal to minus Poisson ratio times epsilon 33. But I know what epsilon 33 is. Epsilon 33 is over here. So this is like that, right? So let me write this same thing over here. So this one is telling me that, and I'm going to leave some voids or blank space over here, that this is equal to minus Poisson ratio divided by E sigma 33. Epsilon 22 is also minus Poisson ratio divided by E times sigma 33, and epsilon 33 is equal to 1 over E sigma 33. You all agree with that? It's exactly the same as that, right? And let's complete here the shear strains. I'm going to have 1, 2, epsilon 1, 3, and 2, epsilon 2, 3. Do I produce any shear strain by applying this normal stress? No, right? So here I'm going to have this is going to be 0, okay? Let me see if well, I can write it 0 times sigma 33. Okay, so those are the equations for one direction. But I can do exactly the same thing in all other directions. If I assume that this rock is isotropic, which means that it will deform in the same way if you apply stresses in any other direction, this is going to deform exactly the same. You will see that here it's going to be the same equations for all the other stresses, sigma 11 and sigma 22. So here I can write 1 over E sigma 11. If I were to apply a sigma 11, I'm going to get an epsilon 11 in the same direction, so this is going to be positive. I'm going to get here the expansion in the perpendicular direction for applying sigma 11. And if I were to apply a normal stress sigma 22, I'm going to get a strain in that same direction with the same sign, and strains in the other direction in the other two directions. And I'm going to get no shear strain. The only way to get shear strains is going to be with the application of a shear stress. And in order to do that, if you apply here a shear stress sigma 12, or a shear stress sigma 13, or a shear stress sigma 23, the strain, which is going to be the result of that, is going to be 1 over G, where G is the shear modulus, divided sigma 23. And now, those are all equations, 6 equations, in order to find this relationship between stress and strain in 3 dimensions for an elastic linear isotropic solid. Any question about those equations? You will see that they are quite important. We're going to solve several problems later on with this. Yes? Is
that 1 over G?
Yes, it's 1 over G. Yeah, this is G. Where G is the shear modulus, and I'm going to tell you in a bit what that shear modulus is going to be. if I remember correctly, I'm going to check this later, okay? But G is equal to Young modulus divided 2 times 1 plus Poisson ratio. So actually, and that's a good question, because it reminds me to emphasize that, remember that in our test we measure Poisson ratio and E and the Young modulus, right? And those are just 2 coefficients. The shear modulus, it's just easier to write it like this, but it's actually a combination of those 2. If you know Poisson ratio and you know Young modulus, you also know shear modulus for an isotropic rock. So that's all you need, just 2 parameters for linear isotropic elasticity. So these equations are all the equations that you need. Let me write here. So this will be what sometimes called generalized Hooke's law in 3 dimensions, and this is valid for an isotropic linear elastic solid. The only thing I'm going to do now is to write this set of 6 equations as a multiplication of a matrix times a vector. Why I do this? I do this because computers like matrices. And if you were to apply this into a computer code, you will put it as a matrix and as vectors rather than as equations. It's much easier to work like that. So if, for example, I want to write L07-1. L07-1, you see, in order to get that one, I just have to multiply these 3 coefficients to those 3 ones. So this is going to be 1 over E minus Poisson ratio divided by E minus Poisson ratio divided by E, and no shear stresses. So this is going to be all zeros, and it's going to be exactly the same for the 2 other equations, where this is 1 over E minus Poisson ratio divided by E, and this is 1 over E. And well, for the sake of completeness, let me write everything here. And this is going to be 0, 0, 0, 0, 0, 0. And if you look at this equation, there is just one stress that can cause that strain. So this is going to be all zeros, but the term in which you have the stress in that same direction. So 1 over G, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0,